Now I'm going to show you one of the interesting application of PCA. So sometimes you have data that has a lot of features in it. In other words, you have a lot of dimensions and it can be hard to visualize. So using PCA, you can actually project it to the lower dimension, maybe to two dimension, and then from there you can visualize your data. It can be a little bit easier to understand the data. So let's look at the first example where I'm converting a 784 dimensional data to two dimensional data. Now I import my necessary libraries. So first I import my PCA. This is responsible for performing component analysis. And then I'm doing also importing my PLT. I'm also importing fetch OpenML. This will allow me to fetch my MNIST dataset. So I'm fetching my MNIST dataset using this inbuilt method, passing my argument MNIST 784, and then it returns my X, which is my feature space, and value Y. And I want to see what shape my X is. And as you can see, it has 70,000 rows and 784 columns. In other words, there are 70,000 images and there are 784 dimensions to each image. Let's take a look at the first data, just the first image. So in this case, I'm printing my X0. I'm just accessing the first index. So when I print it, you can see this one actually has almost a shape of a 5. Let me decrease the size, and there you go. So now you can see that if you look at the outline, it almost has like a 5 to that. We see that. So this is your from the MNIST dataset. Okay, then I do my principal component analysis. Let me increase the size of this. Okay, then I do my PCA on this, and this time I just want only two components. And then I pass my X to the fit transform. This is the inbuilt method. And then I'm printing my principal component this time just for the first image, this one right here. Okay, and as you can see, it converted the 784 dimensions to just two dimension. And these are the two numbers in the two dimension for the first image. Okay, and then now I'm plotting them. So when I plot them, you can see that in a lower dimension, it's not like extremely good. It's not like very highly accurate, but still it does a pretty decent job. You can see that in two components, like visualizing the 784 dimension into two dimension, it is a little bit not very easy, but still you can make out few things. You can see like these clusters, they're hanging together. You can see like 1, 2, 3, 4, 5, 6, 7, and I think I can determine like 7 or 8 different like points over here. So it seems like you can find 7 or 8 different clusters over here. All right. So let's project our three-dimensional data to two-dimensional now. So in this case, uh, again, I'm importing my matplotlib. This time I'm importing make Swiss roll. And what this is responsible for is making a data set. So this is going to make your Swiss roll data set. And in this case, it's going to be three dimensions. So I'm printing my shape. There are 20,000 data points in it. And each data has three dimension, or in other words, three columns. So let's see the first data. Let's take a look at how it looks like. So I'm accessing the first data using my indexing x0, and this prints out my first data right here. As you can see, it has three dimensions. Okay, now I apply my PCA, and I'm using only two components. I pass in my x to in order to find those two components, and then I'm printing my first data of my PCA. So this is the principal component. This is my first principal component, and the second component is right here. Okay, so this has converted into from 3D to 2D. Now let's plot my original 3D Swiss roll, and I'm also plotting my 2D PCA for visualization. So you can see this is your original 3D Swiss roll, which is a little complex and all intertwined. On the other hand, when you look at your two-dimensional PCA, you can see that the data is kind of like flattened out, and you can actually separate it easily over here. So this is one of the advantage of PCA. Okay, let's try to visualize a four dimension now. So I'm going to project four dimension to two dimension using PCA. So in this case, I'm using iris dataset. I'm loading my iris dataset, and my X is the iris.data, and I'm printing the shape of my data right here for iris. And you can see the feature of my feature space is 150 rows and 4 columns. In other words, 4 dimension. So let's take a look at the first data. So first data you can see is 5.1, 3.5, 1.4, 0.2. So these are the four values in the for the first data. The first data has four dimensions. So in this case, I use PCA and I'm specifying my number of component as 2. So this will reduce from 4 dimension to 2 dimension. And then I'm printing my first data point. And as you can see, it has reduced into 2 dimension now. And then I'm plotting my picture. So this time I'm plotting my PCA. And as you can see, oh, let me just come down here. I did not, let's run this cell real quick. Come down here, run this, and run this. And let's run this now. And as you can see that it's able to do a pretty good job. You can see that like your Satosa, they're all cluttered. They're all basically over here, well separated. You see there. So this is my this is my PC1 component right here. This axis is PC1 and this axis is PC2. And then your versicolor, look at this versicolor. It's again well separated from the others too. And then you have another one, which is this one right here. This is your Virginica. So you can see that there is a very well separation between Setosa and the other two. And versicolor Virginica, there is some separation, and you are able to find the separation using by projecting this in a lower dimension. All right, students, I hope this session helps. Thank you.